Hello APE students, welcome to your first video of the year. This video is going to be on Chapter 3, focusing on Module 6. So let's get right to it. Ecosystem ecology is the theme that's going to bind together Modules 6, 7, and 8. So what is ecosystem ecology? Well, it examines the interactions between the living and the non-living world. So we've got nutrients, we've got energy, we've got all the different cycles going on, and they're going to interact within each of these ecosystems in different ways. So going back to the basics, what's an ecosystem? An ecosystem is a particular location on Earth distinguished by its particular mix of interacting biotic and abiotic components, things that should be pretty familiar given your experiences in living environment last. An interesting thing to think about is the boundary of an ecosystem. Where do these things start and where do they end? Caves and lakes are pretty easy in terms of answering that question. If you're in the cave, you're in the cave. And as soon as you get outside of the cave to the outer area, you're outside of the cave. That's a very easy to distinguish boundary. But think about a forest. Think about a wooded area in your backyard. Is that all there is in your backyard? Does it extend out? Does that ecosystem go further into your neighbor's yard? That's hard to say. When looking at the size of ecosystems, though, they can be either very big or they can be very small. If you take a look at the Greater Yellowstone ecosystem, which is shown in that picture on the left, you'll see that there is a huge area, an enormous area, where they have said that is an entire ecosystem, seen by the boundary that's left in orange. But on the right, you can see that there is a small accumulation of water that's inside of a tree, and that has its own ecosystem, right, of all the things that can live within that watery environment. And that's very different than the area around it, which is most likely some sort of deciduous forest. But the complexity doesn't end there. Even though it is helpful to distinguish between two different ecosystems, ecosystems are always going to interact with other ones. Earth and all its ecosystems are open systems, so they are going to share species. They're going to share abiotic factors, such as water that might run downhill from a forest into a lake. So they are all connected. And where it can be seen, if there is an area where you can find that these two ecosystems are connected, we call that an ecotone. Going back to that idea of systems, there are a few things that should be seen. So for example, there is the body of water that in the left-hand picture does not have energy going into it, which would be a closed system. Again, it is not exchanging energy, even though the sun is trying to beam its rays into it. It is not going to work, and all energy inside is stuck there, hence closed. Or it can be open, like in the right-hand picture, where you can see that the sun's rays are entering and heat energy is leaving that water. Now, it's important to think about the energy that's coming through Earth's open system because Earth is really powered by the sun. All things that are eating food are all really being powered by the sun. Look at the picture. You've got the sun beaming down its energy down into the producer. The producer is going to make sugar and grow, and it's going to feed the primary consumer, and so on and so forth. So since the producers are the ones that are taking all the energy from the sun and really establishing the base of our food web, it's really important to look at how productive an area is. So there are a few terms here, gross primary productivity and net primary productivity, that can be helpful in telling us how well an area can generate life. If the producers are able to be very, very successful in taking in that energy, and there's a lot of energy available, there's going to be a lot of food left for the consumers so that they can grow numbers and so on and so forth. So let's dive into these terms a little bit. Gross primary productivity, the total amount of energy that plants capture and assimilate in a given period of time. So this is the total amount of energy before anything happens to it that a plant is taking in and actually obtaining. There's a lot that a plant does not get, which we'll get to later, but this is the amount that it is actually capturing. Net primary productivity represents the rate at which organic material is actually incorporated into the plant tissue for growth. So in other words, plant growth per unit area per time. So this is how much that it is actually building up. And so if you look at the bottom equation, that your gross primary productivity minus respiration is going to give you your net primary productivity. So this is the total amount of energy that the plant is getting from the sun minus the amount of energy it needs to take out from respiration is going to lead to how much the plant is actually growing, or in other words, again, the NPP, net primary productivity. Questions may ask something about the availability of food that is stored in a plant. The NPP is the only available food, as it is what's left over after the energy that's already used from respiration. So this is a very, very important thing, and something that I've already seen in a few of the new questions that they've put into the APES curriculum. They're asking how much is going to be available for the primary consumer. The answer will always be the net primary productivity. Biomass is a term that's always going to come up when we're talking about GPP and NPP, mostly because the NPP, that growth of the plant, is referred to as an increase in biomass. So the energy in an ecosystem is measured in terms of biomass because that's the energy that it is storing, like when we eat lots of food and we store it as fat, if you would like to think of it that way. Also, another term that will come up a lot is standing crop when we talk about agriculture or something where we're talking about lots of plant life in an area. It's the amount of biomass present in an ecosystem at a particular time. So going back to how efficient GPP and NPP are, let's take a look at this picture. So you can see GPP right next to it. It says 1% of solar energy striking producers is captured by photosynthesis. 1% of all the sunlight that is hitting plants, generally speaking, is all that's taken in by them for energy. It's not all of it, it's only 1%. That is very, very small. 99% of it then is reflected or passes through without the producer absorbing it or being able to use it at all. And then 60% of GPP, usually, is lost to respiration. So what do you get left with? Well, you get 1% of all the sunlight that hits an area from GPP, and then you're going to lose 60% of that. So that leaves you with 40% of GPP, which supports the growth and reproduction of the producers themselves. NPP equals GPP minus respiration loss. That's something to definitely know for the test. Efficiency is one that I don't believe is going to be directly brought up, but it is also something we're going to practice and make sure that we are proficient in, which is the NPP over the entire amount of energy multiplied by 100 to figure out how efficient we really are at getting that energy. In the last slide, it said, we got 1% from the sun for that plant, and then we lost 60% to respiration. This isn't true across the board. Different plants are going to have different rates of respiration. Different plants are going to be able to absorb differently. So it is important that we do look at efficiency. And again, we'll do some more problems in class, but I just wanted to put up the equation here so you had a reference. Here is a bar graph for the estimated annual average NPP, again NPP, in major life zones and ecosystems. So I'm sure that if you closed your eyes and thought of places where there was a lot of plants and a lot of plant growth, you definitely would have thought of a few of these, right? Tropical rainforest makes a lot of sense. A lot of trees, a lot of ivy, the canopy, the low shrubs. There's a whole bunch of plant growth that occurs there. But swamps and marshes also, with their algae, their trees, their shrubs, they're also going to have a whole bunch of NPP as well. Next to that, we've got the temperate forest, which is like the area we live in, and then you see that there is a huge decline from that to the taiga, to the savanna, to agriculture. The top ones are definitely something that you should remember. Now, in terms of the non-terrestrial, or the ones that are not on land, if you're looking at aquatic or marine ecosystems, estuaries are definitely the leader in productivity. They're an area that's full of nutrients, they're open to sunlight, so they're going to have a lot of growth. Lastly, I'd like to just go over quickly the energy flow that happens within a trophic pyramid. Here we can see the rule of 10, right, where you lose 90% of the energy that you get from eating all the way through on every level. So you see that you start off with the producers, which have 10,000 of the unit that they've put there, which is kilocalories. You lose 90% of that going up to the next level. So you can see that that's at 1,000 with the zooplankton, and then down to 100 with the perch, and then down to 10 with the human. So with each jump that you get, you're going to be losing energy naturally through respiration and other regulatory processes, and you're only going to get 10% approximately through the 10% rule. Now, I would like to point out that the 10% rule isn't true all the time. There are, again, circumstances in nature where you're not going to always get a perfect number, right? So you could be getting 15, you could be getting 7%. It's going to be around 10%. But they're definitely going to ask you a question about the 10% rule, so it's good to know.